Ladies and gentlemen, good afternoon. My name is Mengyuan Li. I'm honored and proud to have the opportunity to speak in this meeting. The title of our paper is When CSI Meets Public Wi-Fi, Inferring Mobile Phone Password with Wi-Fi Signals. This work is done by Mengyuan Li, Yan Meng, Junyi Liu, Professor Hao Jinzhu, Professor Na Ruan from Shanghai Jiao Tong University, Professor Xiaohui Liang from University of Massachusetts at Boston, and Professor Yao Liu from University of South Florida. I would like to begin with the research background. Nowadays, smart mobile devices are everywhere. Smartphones, tablets, and many other smart devices have become an indispensable part of our daily life. At the same time, mobile payments is in fashion, such as Alipay, WeChat Pay, and many other online bank apps. With the help of those online payments, people are able to be free from cash or credit cards. Going out with only a mobile phone is enough. Those online payments function including the quick pay in market, money transfer to their friends, and many other online payments such as game payments. Take Alipay as an example. In year 2015, it has more than 900 million users, and per day it will have 100 million transactions. The sum of 2050, it has $1 trillion transactions. So, how to keep online payments secure is really important. There are mainly three ways in industry to help protect online payments. The first way is encrypted transaction. All transmission between user and the server is encrypted by TLS and SSL. Because this encrypted transmission, even a malicious Wi-Fi hotspot cannot steal the user's password or analyze the network traffic. The second is a 6-digit password. For Alipay, WeChat, and many other online bank apps, a 6-digit password is required every time people buy something online or transfer money to their friends. So this can make sure that users' money is safe even if the user lost his phones. The third is a limited password attempt times. Too many wrong passwords will lead to a account lock. Combining those three methods, mobile payments was regarded as secure enough way to protect money transfer online. However, if someone can steal the password in this process, the whole process becomes dangerous. We began to wonder what we can do to steal the password. Because the encrypted transmission, steal password will analyze traffic seems impossible. Then we focus on keystroke inference methods. There are many keystroke inference methods, including those methods in CCS, and but unfortunately, their assumption cannot hold in mobile payment scenario. Then in our paper, we propose a Wi-Fi-based method named the WindTalker. Specifically, it uses channel state information from Wi-Fi to achieve the goal. So what is channel state information? Channel state information was the channel frequency response of wireless signals. It represents the state of wireless channel in a signal transmission process. Since CSI reflects the states of its transmission channel, CSI's value will change when the surrounding changes or some objects moving in the signals or in the surroundings. For Wi-Fi, CSI can be calculated in receiver where methods introduced in Wi-Fi standards like IEEE 802.11n and AC. Using these properties, CSI-based approach has many advantages. It can be device-free and can be achieved by commercial devices. There are many exciting existing papers using CSI in different applications, such as centimeter-level localization, person identification, activity recognition, and keystroke recognition. Ali et al. Proposed a system called Wiki in Mobicom 2050. As shown in the picture, that Wiki tries to distinguish different keystrokes, different inference on CSI on an external keyboard. The performance of Wiki proves the feasibility of using CSI to identify different keystrokes in external keyboard is possible. However, can existing work be applied to infer payment password in mobile devices? there are some fatal shortcomings. The first one is for CSI-based recognition application. It all needs a sender and a receiver Wi-Fi devices, which can hardly be achieved in reality. The second is for keystroke inference methods. Those keystroke inference methods usually just recognize their input, but they have no idea what the input is. Maybe someone is sending a message or inputting a password, but they have no idea what it is. So in our paper, we present WinTalker, a novel keystroke inference framework towards smartphones through Wi-Fi channel state information. It has some features such as it only needs one device to attack, no requirements of victim location between two Wi-Fi devices. It can identify the sensitive input time windows by considering the SSIO traffic and the CSI follow together. It can successfully attack Alipay, the most popular mobile payment system in the world, on several smartphones. This is the outline of our presentation. We will first discuss the motivation part, and then we will introduce WinTalker's attack scenario as well as system design. Then we will show how WinTalker performance in evaluation part, and followed by a case study. In the end, we will conclude our paper. Let's start with the motivation part. We first change the CSI collection methods to get valid CSI data. As shown in the picture, the previous out-of-band keystroke inference model cannot work well in reality. It needs to deploy two Wi-Fi devices, and the distance is too short, like 13 centimeters. Moreover, the targets should be placed right between those two devices. However, in our paper, we present an in-band keystroke model. This model can solve all these limitations. More concretely, we release a few Wi-Fi hotspots to attract a user to log in. After the connection was established, the connected smart devices become a victim for potential password leakage. Need to note that since the hand's motion is right between the transmission channel of the smart device's antenna and the Wi-Fi hotspots, all motions of hand during type will have a direct influence on CSI. Able to get valid CSI, we began to wonder what factors may influence CSI during type in mobile devices. We can first recall a common case in our daily life that when we make a phone call, the phone call quality will be influenced by your hand positions. Just like phone call signals, Wi-Fi signals also have a similar condition. As shown in the picture, when users type in soft keyboard, their hand coverage and the finger motions are two factors influence CSI. Different hand coverage and the finger motion, such as finger click, will cause different and unique CSI change. Let's first show how these factors influence CSI. This picture here shows a CSI stream when continuous pressing different number in a mobile phone from 1 to 9 followed by 0 each for 5 times. When type different numbers, the hand coverage will change. When we continue types the same number, finger will click. In this figure, it can be seen that the different coverage when type different numbers lead to different fluctuation range of the CSI value. When we magnify the CSI change in that figure, experiment shows that finger click has a more direct influence on CSI since it will introduce some sharp convex, which corresponds to the quick click's influence on multipath propagation. We can find that finger click in same number are similar, while CSI shape in different key number differ a lot. The experiment showed hand coverage and the finger motion will have a unique pattern for different keystrokers. Using CSI to infer users' keystroke in mobile devices seems possible. Then we will introduce how our system WinTalker steals users' online payment password by CSI. We will first introduce WinTalker's attack scenario, which include the device it needs and the attack scenario. The picture here shows a real-world attack scenario in a cafe shop. Attacker first hide a computer and release a failed Wi-Fi. The victim finds our failed Wi-Fi and may be connected to it. Then WinTalker works quietly. It records the CSI between mobile phone and the Wi-Fi hotspot. Beyond that, it will also record some traffic data. We use the Intel 5300 network interface card, which was $5 to collect the CSI streams, and the antenna we use is TDJ2400BKC. It is a directional antenna and works in 2.4 GHz and was $20. The total cost of our devices, except a normal computer, is only $25, which means that WindTalker is really a cheap attacker. Then let's see how WindTalker works, and this is WindTalker's system design. In order to make the whole system comprehensive, we need to handle 4 challenges. The first challenge is how to enforce victims' devices to be a Wi-Fi sender. The second challenge is how to locate CSI segments caused by password input. The third is how to reduce noise in CSI data, and the last one is how to infer password using CSI. Our system, WindTalker, put forward 4 modules to handle these 4 challenges. It was CSI collection module, sensitive input module, data processing module, and the password inference module. Let's begin with the first challenge, how to enforce victims' devices to be a Wi-Fi sender. We introduced CSI collection model. So how to collect CSI from victim? CSI is extracted from Wi-Fi packets predominance. If we want to obtain CSI, what we need to do is obtaining enough Wi-Fi package. We use ICMP protocol in our model to achieve it. We send the victims' devices an ICMP request and receive the ICMP reply from the phone. We also adjust the ICMP rate to about 800 packets per second, and after that we can get CSI data of 800 Hz. Note that all operation can be done without the victim's awareness, since it will only cost a little network traffic, about 70 KB per second. After that, the second challenge is how to locate the CSI segments generated by password input. We introduce our sensitive input module. Previous keystroker inference works usually ignore what the content they are inferring, or even don't know whether the user is used a PIN keyboard or QWERTY keyboard. In our work, we make full use of our role as a malicious Wi-Fi hotspot and use sensitive input module to focus on online payment password. We make the whole system more efficient. We construct this model based on the following observation, that when users log in an online payment platform, the phone will connect it to payment server. The server's IP address can be used to indicate an ongoing payment. Then we collected some popular payment platforms' IP address as a sensitive pool and use this sensitive IP pool to determine the started and the end time of online payments. The third module, data processing module. This module was designed to remove the noise in CSI stream. We first used directional antenna to remove the noise caused by other people's moving in the public place. In our experiments with 2 additional people moving around, we can see from the left picture, when we use omni antenna, the CSI waveform was dizzy and one cannot see any CSI keystrokers. If we use directional antenna, the result was more obvious. Then we use some signal processing method, including use a low pass filter to remove the most burst noise, and then we handle all 30 CSI streams by dimension reduction using PCA. We can see the results in the figure below. After choosing suitable PCA components, the keystroke waveform was more distinguishable. Then comes the last module, password inference module. This module can be divided into keystroker extraction and keystroker recognition. Well, the rest of the thing is easy to understand. We first extracted waveform change caused by keystroker. For CSI PCA waveforms, we adopt another filter to make the waveform more smooth, and we divided the waveform into many small segments and calculate each segment's variance. The segments containing the keystroker usually have a high variance. Then, after setting a threshold and make some adjustments, we choose the suitable started and end point of each keystrokers. The last thing left is to recognize keystroker. Then we compare the waveform with per collected training data with our testing data to see what the keystroke is. We use dynamic time wiping to measure the similarity between training data and the testing data. As shown in the figure, simple of same keystroke will have shorter distance, while different keystroke will have larger distance. According to dynamic time wiping results, we can achieve password inference. Then let's see how WindTalk's performance. We first focus on classification between different numbers. Is CSI pattern caused by different key numbers large enough to distinguish them? Here, we collected training and testing data from 10 volunteers in 3 types of form. Each volunteer first generated 10 lobs of data, where lob is defined as typing key number from 0 to 9. After that, we evaluated the classification accuracy of WindTalker, so those collected data. The classification accuracies is evaluated in terms of cross validation accuracy. Each time we pick up 1 lob for testing and the other 9 lobs for training. The figure here shows a range accuracy of all 10 volunteers in 10 pin numbers. We performed the evaluation on Samsung Note 5, Xiaomi Redmi Note 3, and Nexus 5. WindTalk achieved a range accuracy of 80 to 73% and 64%. Here, then we concentrated on inferring a 6-digit PIN password. A 6-digit PIN password is a fixed password format for Alipay, WeChat Pay, and many other online bank apps. We give some possible password candidates sorted by possibility and investigate how many candidates can help WindTalker to hit the payment password. For example, if a victim type password 123456, after typing, WindTalker are able to give a candidates list, maybe like this. In this candidates list, the 3rd possible candidates can match the correct password. Using 3 lobs for training 200 passwords from 10 volunteers, in our experiment, if we give 20 candidates, we can hit 50% right password, and if we give 100 candidates, even 80% password can be identified. We continue to do some other experiments about inference factors towards WindTalker. We change the distance between mobile devices and Wi-Fi hotspots. We can find that the accuracy is getting down as the distance grows, but WindTalker can still achieve a high recovery rate even if the distance grows to 1.5 meters. We then change the direction between mobile phone and Wi-Fi hotspots. Because we do experiments, the volunteer used their right hand. So when the antenna was placed in the left side, the accuracy is most high. But the accuracies in other directions is still acceptable, even if the antenna was placed right behind the victim's back. This can be hard achieved by other keystroke inference methods, and it's difficult for victim itself to detect the attacker. Now we introduce a real case study towards Alipay and perform a video demo to help you better understand how WindTalk works. The first part is collected some training data. In this experiment, we only collected 1 lob of training data. Well, in this case, the third candidate can match the right password. Yes, problem. So the case study towards Alipay include 10 password tests. The results shows if we give 50 candidates, 7 passwords can be right identified. Finally, we conclude our work by introducing limitation, countermeasure, and conclusion. WinTalker has 3 limitations. The first limitation is hardware limitation. In the experiment, we use Intel 5300 NIC to collect CSI data. It's a cheap device which only worth $5, but it will crash sometimes. The reason why it crashes is because some problem in its drivers. But if we want to fix it, we need to cooperate with the Intel company. The second limitation is a fixed typing gesture. Too quick type or strange hand motion or disturbance nearby, such as you type near a USB fans, then WinTalker will not work very well. The third limitation is user-specific training. In the real-world experiment, it's hard to adapt others' training data to use the WinTalker to infer the password. But in the paper, we introduced several methods, including text captions and plain content analysis to handle this limitation. Need to note that the last 2 limitations are a common assumption for those set channel-based keystroke inference attacker. There are also some countermeasures, such as random layout of keyboard after every click, or change typing gesture by victim itself, although it sounds strange. The last countermeasure can be done by preventing the collection of CSI data in CSI collection module. Then we make a conclusion. We present WinTalker an interesting attack that using physical layer information to attack application in the upper layer. It's expected to have a broad potential application for password inference in mobile devices. Encrypted traffic analysis plus CSI analysis should be cool in the future. The future work is mainly about that in our work, the CSI collection model is not reliable sometimes, so we may try to use USRP to enhance it. Thank you for your listening. I'm ready to take some questions now.